right, thank you for the introduction. So, hello, I'm Sanjay. I'm here to talk about FaCT. It's a language we created for writing cryptographic code and preventing timing side channels. So, what exactly are timing side channels and why are they a problem? So to check that out, we'll take a look at this. So this is an actual snippet of code from the popular cryptographic library libsodium. It's 3 lines long. But what actually does it do? It's kind of hard to tell. What if I instead showed you this bit of code? So it's a lot easier to tell in this bit of code that we're comparing 2 buffers. And this is actually doing the same thing as the previous snippet. And so what specifically it's doing is we're going through element by element, and we're comparing each of these elements. And if we find 2 elements that are different, then we hit this condition, and we're going to return -1. Let's say this takes about 5 milliseconds. But what if instead the 2 buffers were exactly the same? Then we would end up going through all of the elements in the buffer. We wouldn't return until we hit the end of the function, and this might take about 8 milliseconds. So the thing is, we may not just be comparing 2 buffers x and y. What if we're comparing a password and its guess? Then an attacker that's trying to guess your password will see this difference between 5 milliseconds and 8 milliseconds. So if they see that this code only takes 5 milliseconds to run, then they know that they've guessed the first 5 elements of your password correctly. And this is a problem. And the problem comes from this code exiting early based on the contents of this buffer, which is leaking information about the contents. And so we can't write code that does this. So this code on the left, although it's easier to tell what it's doing, it's insecure. Whereas the code on the right, although it's much harder to tell what it's doing, it doesn't have this returning early, and so it's secure code. And so this style of code where we prevent these differences based on timing is called constant time code. And the word constant time is a little bit of a misnomer. What we really mean is that the timing of this code is independent of any secrets. So for this small bit of code, it's already starting to get pretty inscrutable what's going on. For actual cryptographic code where we're doing this, constant time code gets really messy. And because it gets so obfuscated, this leads to real bugs. So OpenSSL had a padding oracle attack where the amount of time that their record validation took to run could reveal your session key to an attacker. And they could go on to man-in-the-middle your SSL session. So this is a screenshot of the patch that fixed this. So in the code, that was patched. Even after the patch, there was still another timing attack. There was the Lucky 13 timing attack. And even after they fixed that, there were still more timing vulnerabilities. And it took them a long time until they finally fixed all of these, we think. So what we really want to do is we want to be able to write simple-looking code that expresses exactly what we're doing and have the compiler take care of producing the proper constant time output. So this is what FaCT does. It's a language where you can write readable code and the FaCT compiler produces constant time output. So in the rest of this talk, I'll tell you what exactly we transform, how we transform it, things we can't or don't transform, and finally, we'll evaluate whether FaCT is a useful replacement for constant time code. So first, what are we going to transform? We could start out by transforming anything that leaks. So we have this conditional branch. It branches on some secret. This will leak this secret value. We can transform this to straight line arithmetic constant time code. It no longer leaks this secret. It's a little bit slower, sure, but we're no longer leaking. However, if we're branching on a public value, we don't really care about transforming this. If we leak a public value, either the attacker already knows what it is, or we don't care if they find out. There's really no point transforming this code. We only need to transform code if it's leaking secret values. So how do we tell what's secret? Well, in cryptographic code, generally the developer knows already what is public and what is secret. So we'll have them explicitly label all of their variables. So secrecy is explicit in the type system. And now the compiler in this example knows that key is a secret variable. And so this expression, key greater than 40, is a secret expression. And so by branching on this, this would be leaking some secret information. So we can detect secret leakage in our programs. There's a variety of ways that you can end up leaking secrets. So conditional branches, early termination, as you saw, function side effects, memory access patterns, just direct assignment if you're assigning a secret value to what's supposed to be a public variable, and so on. And FaCT is going to target these first 3. So we're going to transform your code so that these first 3 methods of leaking go away. And the rest of them we're going to disallow through our type system. And I'll get into why we don't transform those in a bit. So So what we transform. So how do we do the actual transformations? Like I said, we're going to transform these three things. And in this talk, I'll focus on the first two, conditional branches and early termination. So let's say we have this example. If s, some secret, then x gets the value 40. Otherwise, x gets the value 19, y gets the value x plus 2. What we're going to do is we're going to execute both branches, and then we're going to fold the conditions into each branch so that the proper effects happen. So this first branch, we'll transform it like this. And we're going to take this condition, if s, and fold it into our bit hack arithmetic like this. So if s is true, then x will get the value 40 as a result of this expression. Otherwise, x will get its original value assigned back to itself. And similarly for the other branch, if s is false, then x will get the value 19, y will get x plus 2. Otherwise, they get their original values assigned back to themselves. And this is what the final transformation looks like. Now it's just straight line code. We're executing both branches, but we only see the effects of the proper branch. And now that we know how to transform conditionals, we can use that to transform other things as well. So a secret return. So if we have fs, some secret, then return the value 40. We can rewrite this into a conditional statement. So we set up this new variable rval that holds our return value and some additional state that says whether our function is returned or not. And now the return statement becomes, if we're not yet done, then assign 40 into our rval and then set done to true. And then at the end of the function, we return rval. And now that it's written in terms of conditional statements, we know exactly how to transform this. It's the same transformation you just saw a couple slides back. So that's how we do the transformation. So what are things we can't or won't transform? Well, it turns out not all transformations are what we really want to do. So we could have transformations that end up producing inefficient code or transformations that just straight up produce unsafe code. So I'll give you some examples. And so our type system is going to reject these programs. So I told you that memory access can leak secret information. So specifically, if you're using a secret index into an array, then you can end up leaking this secret index. And there is a transformation we could do. We could turn this into a full array scan over the array and use a conditional inside to check that we're operating on the proper index. But now we've turned something that should be O of 1 and made it O of n. And this is pretty bad, especially if you're working with larger buffers. So we're not going to do this transformation automatically. And in general, this is fine, because again, for cryptographic code, you're not typically seeing direct secret indexing on buffers. You're generally only working on public sections of any buffer anyway. And so for stuff like this, we're going to reject these programs instead of transforming them. So even worse than inefficient code, though, is unsafe code. So in this example, we have if j is less than some secret length, then x gets array sub j. We're going to do the usual transformation on this. But remember that we always perform both branches of every transformation. So we're always going to attempt to access array sub j in the transformed code. So what happens if j is actually outside of the bounds of this array? Then now we have an out-of-bounds access. Our compiler has introduced an out-of-bounds access into this code as a result of transformations. And that's really bad. So we're going to augment our type system to check for memory safety. We're going to check every array access for potential out-of-bounds accesses. We're going to use that constraint solver, in our case Z3, to do this. And our constraint solver is path sensitive, except for secret branches. And this is key because remember, after transformations, all of your secret branches go away. So we can't add those to our constraint solver. And so now with this, we can check if your program is going to become unsafe after transformations. And we can reject programs that would become unsafe in this way. So finally, we want to evaluate whether we can use FaCT to actually replace C for constant time code. And there's three big questions we want to ask. Can we express actual cryptographic code in FaCT? Is FaCT code as fast as C? Because generally, you write cryptocode in C for performance reasons. And finally, is FaCT actually more readable than C for constant time code? Otherwise, we've kind of failed at our original goal. This first question, can we express real code in FaCT? To answer this, we ported actual cryptographic code to FaCT. So FaCT is not meant as a general purpose language. We only expect you to port the timing sensitive parts of your code base into FaCT, but there's several ways you can do this. So if your entire library needs to be timing sensitive, then you can port your entire library. You could also take just a function and all of its dependencies and port that into FaCT, or even if there's just a chunk of code inside one of your functions that needs to be timing sensitive, then you can turn that into a FaCT function. And FaCT supports all of this, because our compiler produces C-style object files. And so you can link those into the rest of your code base just like you would any other code. And so we did all of these. We ported the Donna elliptic curve library in its entirety. We ported the secret box API, so it's authenticated encryption decryption from the libsodium library. And we also ported from OpenSSL the record verification chunks of code, so the ones that had all of those problems that I showed you at the beginning of this talk. And so in both the SSL path and the TLS path, we ported just those chunks of code. And so to give you an idea of the amount of developer effort involved, here's a graph of lines of code. You'll notice that FaCT is a tad bit more verbose than its C counterpart. This is because we're more strict about array usages and we don't have preprocessor macros, and that tends to be the biggest reason why. So we were able to port this code, but in doing these ports, like with any sound system, we sometimes had to get around the strictness of our type system. And so there's three ways we allow you to do this. In fact, there's declassify, there's assume, and there's extern. So declassify allows you to take something that's secret and treat it as public. And we had to use this in exactly two places in all of our ports. The first one was in the secret box implementation, where the secret box decryption algorithm will actually verify whether a ciphertext is valid before it will go on to do the actual decryption. And the way its algorithm is set up, it doesn't actually leak anything to return early if verification fails. And so we use declassify here to be able to actually branch on this and truly return early if verification fails. The other instance we had to use this was in the OpenSSL TLS record verification port, where in their algorithm they explicitly use a secret index into a buffer, but they do some tricks with cache alignment so it's not actually leaking anything. And so that trick is made explicit in the FaCT code with the declassify operator. Next we have assume, which adds constraints to our type checker for checking for memory safety. So this was mostly used for setting up function preconditions. So FaCT is meant to be called from C, and so we need to know what conditions you have going into these functions. So about 20 instances of assume for this reason in our code. The other thing we need to assume for is that our solver doesn't actually track values through memory. So if you're using a mutable variable as an index, for example, then the solver needs to know exactly what constraints it has. And so we had about 10 instances of assume for this reason. But finally, we have extern, which lets you call functions that were written outside of FaCT. And we use this in the OpenSSL ports to call the C implementations of the AES and SHA-1 core primitives. We did this because the OpenSSL code that we were interested in wasn't actually the low-level primitives. It was the code that uses those primitives that had the timing side channel problems that we were interested in. And so we were able to call the C functions directly and focus on the porting of the actual timing-sensitive code. So next we want to know, is FaCT code as fast as C in terms of performance? So we had our compiler produce LLVM bytecode, which we optimized using the same optimization flags as the corresponding C code. And we used a tool called DudeCT to check whether our resulting code was constant time. So DudeCT is a tool that runs your program several million times and checks for any statistically significant timing variations based on the inputs. And so we did check with DudeCT, and we're empirically still constant time after optimizations. So compared to C, our overhead is within 5% at worst. And actually, in the case of secret box, we actually were slightly faster. It's because it turns out the FaCT-generated code seems to be better able to go through the vector optimizations that Clang does as opposed to the C counterparts. So finally, we want to know, is FaCT more readable than C for constant time code? And to do this, we conducted a user study. So we had 77 undergraduates in a programming languages course, and we had them do a sequence of tasks to understand and write constant time code. So the first two tasks, we gave them a snippet of constant time code, and they had to tell us what it did. And we scored them 0 to 100. And on average, the students were better able to determine what the code did when looking at FaCT code. So the next three tasks, we gave them a specification, and they had to write code in C or in FaCT that fit the specification. So the code had to compile, it had to pass our correctness tests, and in the case of C, it also had to pass a constant time verification tool. And so they could keep submitting, and we would give them error feedback until they actually passed the task. And we found that students were better able to complete the task when writing FaCT code than when writing C code. You'll notice task 4 looks substantially lower than the other two. We actually had a bug in our framework specifically for task 4, where it was allowing students to pass the task even though they didn't write constant time code. So there were actually only 16 students that submitted constant time code to pass the task. The other 16 did not submit constant time code and were still able to pass the task because of this bug in our framework, specifically task 4. But students were still better able to complete the task in FaCT. So yes, we did find that we were able to express real code in FaCT. It's just as fast as C, and so at least in the case of our user study, FaCT code was more readable than C code. And even though these were students working on small snippets of constant time code, we feel like this does translate to cryptographers working on much more complicated constant time code as well. So in summary, FaCT is a DSL we wrote to let you write readable constant time code. And it does this by transforming your program to be constant time. And our type checker ensures that the resulting program will still be safe. So all of our code is online. That's it. I'd like to open up for questions. Thank you.
Hello. When you do this condition trick, strictly speaking, you go from lazy to strict evaluation. Therefore, not only you can introduce self-defined behavior, but also non-termination. Therefore, you have to check whether your branch terminates. If you have a call to a function or an infinite loop, do you do something along those lines?
Yes. So the FaCT language is actually, the way we've designed the language, because it's so restrictive, you can't have non-terminating code. So the
external function call, right?
Yeah, so up to external function calls, yes. So if you're doing one of those things to go outside the type system, then we can't say for sure that you're doing this. But if you stick to FaCT code, then all loops are bounded and there's no recursion. So, yes.
Hi. I was wondering if there were cases where the compiled, I'm assuming you compiled to assembly,
Yes.
essentially, right? Where there's maybe some data dependence from the instruction set or some cache behavior that can cause them to not be constant time. I know you checked it empirically, but can this ever
Yes.
escape the type system?
Yes, so it's mainly based on just looking at our code generation manually for these ports and the empirical testing. So like I said, the FaCT system is pretty restrictive. So there's only a few different things that we actually generate. And based on what we've seen, the code generation from that going down to assembly doesn't do anything that becomes non-constant time again. Yes, thank you.
Do you guys deal with any function recursion, which might have some time internal?
Yes, so FaCT, we just sidestep that entirely and we disallow any sort of recursion. So usually you don't need that in cryptographic programming anyway, so yeah. Thank you.
No more questions? Let's thank the speaker again.
Thank you.